Hello again. This is Math 2232 coming to you from the College of DuPage. The title of this lecture is Polar Coordinates, Equations, Graphs, and such. Please be attentive while watching this video. By way of introduction, many calculus courses at the College of DuPage include analytic geometry in their title and curriculum, and this was included. So in addition to teaching you about the calculus of polar coordinates and polar equations, we're going to teach you about the analytic geometry associated with them as well. Now, I have found that students often find themselves confused, so I want to underscore at the outset that there are differences between polar coordinates and other coordinate systems and parametric equations. Some of these differences are subtle, and some are fundamental. But polar coordinates is not just a parameterization. Okay, so a lot of times we will just have the x, y rectangular coordinates or the Cartesian coordinates that you often will talk about. Polar coordinates are completely different. We're going to have r, which is the distance, and we're going to have theta, which is an angle. So what happens is the coordinate system is different. Here you see we can measure this is 1 unit, this is 2 units, this is 3 units, 4 units, 5 units. So we're going out along this ray, and that is distance from the origin. But also we have an angle which tells us the direction that we're going. In this case it was pi over 4 in radians, or it would be 45 degrees in degrees. So you see right away you're saying, oh, this is a totally different coordinate system. It also is really different on your calculator. If you hit the function mode in your calculator, you will get a screen that says, well, I'm going to be graphing these assuming that y equals f of x. Now, y is not always equal to f of x, and sometimes y is not simply f of x. It can be more complex, but here you're assuming that y is equal to f of x, and this is something that you often will do. That's the functional or Cartesian kind of screen, assuming y equals f of x. We just finished studying parametric equations, and you can do parametric equations in 2 dimensions, but now things become a function of t, and this is quite a general approach because here you don't have to have y and x having a functional relationship between the two. But today we're going to talk about polar coordinates, or POL, in your calculator, and we can either be radians or degrees here. Now, this is what comes up whenever I go to do something. And again, this particular thing is saying that r equals g of theta, or r is a function of theta. Is it always simple to be a function of theta? And the answer is no, but it's a similar kind of assumption for this. So you see it's a very different setting even on your calculators. Okay, that's probably enough introduction. Up to this point, we've dealt exclusively with the Cartesian or rectangular XY coordinate system. However, we see this is not always the easiest coordinate system to work in. So in this section, we'll start looking at the polar coordinate system. Now, coordinate systems are really nothing more than a way to define a point in space. For instance, in the Cartesian coordinate system, at point given by xy, it looks like this. You go out a distance x here and up a distance y, and that tells you where the point is. But that's not the only way to define a point in 2-dimensional space. Instead of moving vertically and horizontally from the origin to get to the point, we could instead go straight out from the origin until we hit the point, like this. And then determine the angle that this line makes with the positive x-axis. We could then use the distance of the point from the origin and the amount we needed to rotate the positive x-action as the coordinates of the point. So the same point, you can see this is the xy, and this is intended to represent the same point, is now represented by r theta. Coordinates in this form are called polar coordinates. And the reason they're called polar coordinates is that the origin sometimes is also called the pole, and this has to do from geography or astronomy or what you want to say, but that you could think about this as being a North Pole. The above discussion may lead one to think that r must be a positive number. However, we also allow r to be negative. Below is a sketch of 2 points, 2 comma pi over 6 and minus 2 comma pi over 6. And I tell my students to think about the car is pointing in the direction of theta. So the car is pointing in the direction of pi over 6. But your car has a forward gear. It also has reverse. So even though the front of your car is pointing in a direction of pi over 6, you could have it in a forward gear or a reverse gear, and you would land at different points. Now these two are different points, but what I want you to realize is that r can be negative. I think I talked about all of that. Okay, this leads to an important difference between Cartesian coordinates and polar coordinates. In Cartesian coordinates, there's exactly one set of coordinates for any points. With polar coordinates, this isn't true. In polar coordinates, there are literally an infinite number of coordinates for a given point. For example, we say 5 pi over 3 is the same as 5, and this is minus 5 pi over 3. Let's talk about that. So you see you can go and be outgoing 5, and this is pi over 3, but that is the same direction as we went negative, minus 5 pi over 3. Or we could point at 4 pi over 3, which is over here, but we could put it in reverse and get minus 5, which is land us the same point. And similarly, both of those could be negative. And so what we could do is we could say we're going negative 2 pi over 3, and we're going in a negative 5 direction, and see all four of those land you at the same point. And you might say, well, where's the rest of the infinity? Well, we could go around many times and land at the same point. Okay, and this was really talking about that the r theta is the same as r theta plus 2 pi n, where n is an integer, or this is the same as minus r, and this is theta plus 2n plus 1, that's an odd multiple of pi, where that's an integer. Now, we also should talk about the origin of the coordinate system. In polar coordinates, the origin is often called a pole. I already talked about that. Because we aren't actually moving away from the origin at the pole, we have r is equal to 0. However, we can still have your car pointed in any direction and still be there. So the coordinates are 0, comma theta, where theta is any. And that's the same sketch we talked about before. Now that we've got a grasp on the polar coordinate system, we need to think about converting between the two coordinate systems. We've talked about the rectangular or Cartesian coordinate system and the polar coordinate system. So recall that we call this point x, y, because you went out x here and up y, but also this is called r theta. Well, you've got a right triangle there, and so it's very easy to get these equations. X over r is equal to the cosine theta, so that means x is equal to r cosine theta, and similarly y over r is equal to the sine of theta, so y is equal to r sine theta. And sometimes, not always, but sometimes the radius or r is a function of theta. Other times it's just an r, and you have to be careful. But sometimes if r actually is f of theta, then we would find that x is equal to f of theta times cosine theta, and y is equal to f of theta sine theta. We'll talk about this more later. Okay, so you see here, this allows us to say, if I know r theta, I can figure out x and y. Now, converting from Cartesian is almost as easy. That means you're starting with x and y. What do you get there? And again, these conversions should be committed to memory. So just notice this, that x squared plus y squared up here is going to be r squared. You see r cosine theta whole squared plus r sine theta whole squared ends up being r squared times some trig identity that is 1, so that is just r squared. And if we take the square root, we find out that r is equal to the principal square root of x squared plus y squared. Again, it could be positive or negative, but this gives you the absolute value of that. And they say technically they could be a plus or minus and so on and so forth. And then if we take y over x, what we get is r sine theta over r cosine theta. The r's cancel and that becomes the tangent. So y over x is equal to the tangent of theta, and if we take the inverse tangent of both sides, we get that theta is equal to the inverse tangent of y over x. You want to commit these to memory. Now, you do need to be careful with this because inverse tangents only return values in the range of minus pi over 2 to pi over 2. That would be the first and fourth quadrants. But there's a second possible angle that is possible when you get that, and the second angle is given by theta plus pi. Now, I am going to tell you right now, this is a very important issue for scientists and engineers. This comes up in differential equations when we're determining the phase angles, and when you get to that course, for sure, you will see this again. So anyway, here is the formulas, again, to be committed to memory, that allow us to change Cartesian coordinates into polar coordinates. This means you're given x and y, and you got to find r and theta. So we know x and y, so r is equal to the square root of x squared plus y squared, and theta is equal to the arctangent of y over x. Here's a problem for you to practice this. So I'm asking you to convert each of the following points to the given coordinate system. So here we have minus 4, comma 2 pi over 3. This is given in polar coordinates, and you want to turn it into Cartesian coordinates. And here you have minus 1 in Cartesian coordinates, and you're turning it into polar coordinates. You might want to note that I have to tell you when I list this, this actually could be in the xy coordinate or polar. So I do have to tell you that. But I have told you that, and so now you know what to do. Let's see how you did. Okay, well, we're just using those formulas that I said you should commit to memory. So x is equal to r cosine theta, and the cosine of 2 pi over 3 is also negative, so negative 1/2, so that is minus 4. That's minus 1/2, so that is 2. And y similarly is minus 4. This is the sine of 2 pi over 3. It is this, and that is negative. So you see that this, those are the equivalent coordinates. So the Cartesian coordinates is 2 comma minus 2 square root of 3. Now I also ask you to convert this one, and if we do that, we will first find r this way. It's the sum of the squares. It's going to be the square root of 2. And now get theta. Well, theta is the inverse tangent of this. Now the minus over minus is plus, so that is going to be pi over 4. Now, this is not the correct angle. You see that already, because this would give us a theta in the first quadrant, and the point we've been given is in the third quadrant. So you see we have to add pi, and so we're going to get 5 pi over 4 for this. So in polar coordinates, the point square root of 2 comma 5 pi over 4 is the answer. Notice, well, we could have used a different theta. We could have used the pi over 4, but then we would have minus here. So, you know, either of those answers would have been correct. Here's another problem for you to consider. We can also use the above formulas to convert equations from one coordinate system to another. And so here I'm asking you to convert this equation. This is a nasty cubic, actually, into polar coordinates. And then the second one, I'm asking you to compute this, r equal minus 8 cosine theta, into Cartesian coordinates. And you want to be picking points and so on and so forth. You know what to do. Let's see how you did. Well, here we really just have to substitute. Everywhere we have x, we write r cosine theta. And everywhere we have y, which is over here, we write r sine theta. And so this is what we get. And we do just a little bit of algebra, but not very much. We simplify and combine like terms, but this is the answer to that problem. Notice that it would be very hard to solve this for r, though. So in this case, you probably would not be resorting to r equal f of, or g of theta. The second one, though, we're to convert r equal minus 8 cosine theta into Cartesian coordinates. Well, remember that r squared was, r squared is x squared plus y squared square root whole squared. So that is x squared plus y squared. And minus 8 is minus 8, but r cosine theta is x. So you see we get x squared plus y squared equals minus 8x. And you might say, okay, I changed that into that, but what is that geometrically? Well, I can complete the square, and so I move everything to the same side setting equal to 0, and I complete the square by adding 16 to both sides, and so I have this equation is x plus 4 whole squared plus y squared equals 16. So you see this really was a circle of radius 4 and center minus 4 comma 0. We'll say much more in the next video, but in closing for now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. Until we meet again on the next video, take care and may God bless you.